In this video, we continue with Chapter 2.6 and take a look at applications to economics models. Our learning objective for this video is to use matrix algebra to analyze an economic system. In this case, we're going to look at the Leontif input-output model. So in economics, an input-output model where the input from the supplier is over here in the rows and the output from the user is here in the columns. This is known as an input-output model, and it was developed by Leontif, who won the Nobel Prize in the 1970s for this work, the prize in economics. And it consists of n different industries, each identified as IN, I is for industry, each of which needs inputs. So in the example we're going to use steel, food, and labor, and the industry has an output to the user. So to produce a unit, for example, say $1 million of output, an industry may use the outputs of other industries and of itself. So this is why we need a complex system in n dimensions. For example, production of steel may use steel, food, and labor. So we're going to let each entry Dij correspond with the amount of output the industry J needs from industry I, because J corresponds with our columns and I corresponds with our rows, and our rows are the suppliers and our columns are the users. And so these entries Dij, so the output industry J, the columns need from industry I, the rows, to produce 1 unit of output per year. We are going to assume that these are fixed prices, so our values are going to be constants. We're not going to have variables inside our matrix. And so the matrix of these coefficients is called the input-output matrix, or the consumption matrix D. A column represents all of the inputs to a given industry. So each industry corresponds with a different column here. And then for this model to work, the sum of each columns has to be less than or equal to 1. Otherwise, it costs more than 1 unit to produce a unit in that industry. So all of our values here are going to be between 0 and 1. And then we're going to let X sub I be the total output matrix of industry I, and we'll call matrix X all these Xi entries. It'll be columns. So if the economic system is closed, self-sustaining, then the total output equals what's known as the intermediate demand. In other words, what is needed to produce it. Then in those cases, X equals dx. So our matrix D, our consumption matrix, multiplied by the output matrix. If the system is open with external demand matrix E, exports, then our matrix X equals dx, the consumption matrix times the output matrix, plus the external demand, the exports matrix, E. So to find what output matrix is needed to produce a given external demand matrix, we solve this equation, X equals D plus E. So we can rearrange. You see in the first row here, I've isolated E. So we have X minus DX equals E. And remember, these are all matrices. So we'll be able to subtract the matrices because we are working with dimensions that are going to work together. We've got n by n matrices for D and E, and then X is a column matrix that is n by 1. So the multiplication will work, no problem there. All right, so then we've got X minus DX equals E, and then we can factor out the X. So we'll have the identity matrix minus D times X equals E. And then to isolate X, we're trying to find the needed output matrix. We can say X is going to equal I minus D inverse multiplied by E. So let's take a look at an example here. So in this matrix D that we're going to build, we know that production of 1 unit of steel requires 0.4 units of steel, no food, and 0.5 units of labor. So in our matrix down here, I'm going to let the first column and the first row correspond with steel, and the second column and the second row are going to correspond with food, and the third column and the third row are going to correspond with labor. And remember, the rows correspond with the supplier and the columns correspond with the user, the output. So this is our input here. In the rows, and our columns are the output. All right. So this is our consumption matrix, D. So to keep building it, we are going to add in the fact that production of 1 unit of food requires no steel. So in the food column, steel row, we have a 0 there. 0.1 units of food, so the food column, food row has a 0.1 there. And 0.7 units of labor, so the food column, labor row has a 0.7 there. And then to fill in the last column, we use this given information that production of 1 unit of labor requires 0.1 units of steel, 0.8 units of food, and 0.1 units of labor. So now we want to find the output matrix. So we are going to work this equation, X equals identity matrix minus D. We're going to invert that, multiply it by matrix E. Oh, where's matrix E coming from? That comes from the fact that our external demands are 300 units of steel, 200 units of food, and no labor. So matrix E is this 3 by 1 matrix, 300, 200, 0. And so we can head into Simpy and do all that multiplication. And you can see how we get these results here. Okay, I'm going to start by entering matrix D. Second row of matrix D is 0.1.8. And third row of matrix D is 0.5, 0.7, and 0.1. We can type D enter just to check and verify. That's a match for our matrix. And then we are going to enter the identity matrix. So we'll say identity matrix is going to be 1, 0, 0. This is a 3 by 3 identity matrix. It's probably also default coded in here. So you can go Google search what's the default code for the identity matrix. All right, there's our identity 3 by 3 matrix. And then matrix E is a 3 by 1 column matrix, and that is 300 units of steel, 200 units of food, and no labor. And we can check matrix E. All right, so our matrix X is going to be I minus D inverse. So let's see if I can do that. Let's see, I think I have to give it a name. We'll call it G equals I minus D. There we go, okay. And then I think we get G inverse by doing G exponent -1. Voila. And so we're going to then do G inverse times E. So we'll do G exponent -1 star matrix E. And there is our matrix X. And so if we round to the nearest whole numbers, we'd say we have 848 units of steel, 2,076 units of food, and 2,086 units of labor. And that's an exact match for our results here in the last column. So you can see how we can use Simpy to do these calculations and conclude that we need 848 units of steel, 2,076 units of food, and 2,086 units of labor. So you can imagine how useful this is for business models, or if you think about how restaurant supply chains work, they do these exact same kind of multiplications with matrices and using linear algebra and sophisticated computer systems. So the restaurant chains that are all owned by the same company, like Red Lobster and Olive Garden, and I think Cheesecake Factory is part of the same big company. They set up these supply chain models so that they can efficiently deliver the food needed for each day at the different restaurants in their supply chain. And it's really efficient for them in terms of operating as a big company. Okay, in the next video, we are going to take a look at the line of best fit.